Okay, hello and welcome to this, our final CertiCAV webinar. Thank you for joining us today from wherever you are. I see we have registrations from all over, so good morning, good afternoon and good evening. My name is Richard Holland. I head up the Regulation, Safety and V&V team in the New Mobility Technologies Directorate here at Connected Places Catapult. I'm going to briefly introduce you to today's program before handing over to the speakers for the day. We're going to give you a final update today on the project and share with you some details of the outputs that the project team has generated over the last 12 months. So, delivered by the Catapult and Warwick Manufacturing Group, the project has been funded and sponsored by the UK's Department for Transport. We've also had fantastic support from the Centre for Connected and Autonomous Vehicles and the CAVPAD programme. And I must also thank the VCA and Innovate UK who have provided valuable input and direction throughout the project through their participation in the project steering panel. So here on the screen is a reminder of the goals that were set at the beginning, which Zane is going to talk about a little more about later on. We'll show you what's been achieved to meet these goals, and we'll explain some of the resulting concepts that have been developed. So here's the plan for the session today. So I'm delighted to welcome Pete Newton from the Department for Transport, who will talk to us in a few moments to get the afternoon started. Zane's then going to give an overview of CertiCAV as a reminder or as an introduction to those who are unfamiliar with the project. Tom's then going to talk through several technical topics which are key to the CertiCAV framework. And then after a quick break, Siddhartha from WMG is going to talk about V&V. And then when Tom has then told us about independent assessment, Rob and Sam are going to demonstrate a practical application of some of the framework's concepts which have been presented today. There'll be a Q&A session before we close, which I'll moderate. So please use the Q&A function in Zoom throughout the afternoon presentations. Some questions might be answered directly in the Q&A window, but most will be answered by the panel at the end of the day. If you want to ask the question specifically to one member of the team or the panel, please indicate this and who you'd like it addressed to in the question. Otherwise, I'll pick someone to answer it as appropriate. We might not have time to answer all of your questions live, so apologies if I don't get around to yours today. In that case, we'll endeavour to publish written answers to as many questions as possible and circulate them after the event. So that's enough from me, and I'll now give the virtual floor to Pete Newton. So welcome, Pete.
Hi everybody, hopefully you can see my screen. As Richard introduced me, I'm Peter Newton. I work as in the Innovative Mobility team within the Department for Transport as part of Vehicle Standards. And as the name suggests, we look at technical standards for new and innovative modes of transport, including automated vehicles. So today I'm going to talk to you a little bit about the approval process and the approval process for conventional vehicles and how we might need to change that for automated and specifically highly automated vehicles. So the UK and this government in particular are really ambitious to be at the front of technological innovation, and this includes all sectors, but in particular automated vehicles are really a flagship item, and we're really very keen to realize the benefits that they'll bring as soon as is possible, but we don't want to do that at the expense of safety and security. And with automated vehicles, that's essentially the question we're trying to answer at the minute, is how can we allow them on our roads and ensure that they meet all the requirements that we would like them to, and don't pose extra risks, but we actually realize the benefits of increased safety that we should get from them in the end. So what we need to develop is an approval scheme for highly automated vehicles. And so you can see the first 2 points there. Firstly, we'll have to develop a set of technical requirements that we would like them to meet. And then before we allow them to go onto the public roads, we'd have to have a series of suitable tests that we can subject the vehicles to, so that we know they meet the required standard. And those first 2 points really describe the type approval framework that we work to at the minute for conventional vehicles. And by conventional vehicles, I mean vehicles without any automated capability. And so in the current type approval framework that we use, there is a list of technical regulations that the vehicles have to meet in order to be approved for sale. And there are technical regulations for all sorts of things on vehicles, so everything you'd expect, from braking to steering, collision protection, emissions, and then even things like seat belts and seats and electromagnetic compatibility. So it's not even regulating conventional vehicles. It is not a straightforward exercise. And in fact, you'd probably find if you printed out the requirements for a normal passenger car that you see driving around on the streets, you would end up with quite a large stack of paper just for a normal vehicle. And this gets much more complicated when we're dealing with automated vehicles. So a technical regulation, they're all roughly the same in layout. It will give you the technical requirements, and then further down it will tell you which tests a vehicle has to go through to ensure it meets these requirements. And again, with conventional vehicles, that can be usually fairly prescriptive. So for example, in terms of something like electronic stability control, you can think of the worst case scenario and ensure that the vehicle is able to cope with that. So the worst case scenario is a driver going from full lock one way to full lock the other way and back again. And so they essentially test that scenario, and if the vehicle doesn't skid off the road or topple over, then it meets the requirements for the stability control. But when we start to talk about automated vehicles, it becomes a lot more difficult, because the problem is so much more complex with so many more degrees of freedom. It's difficult or impossible to narrow down those worst case scenarios that the vehicle has to deal with. And we have to start thinking about things like functional safety, and these aspects become much more important, and how the vehicle will behave in certain situations, and the very complex code that drives how the vehicle performs, which is millions of lines of code, and how do we ensure that that code all works as it should do and works as intended, and even to ensure that the intended function of that code is safe, and you know, it would be easy to overlook certain aspects of the system. So it's this is the challenge that we're dealing with now. So some of you may have seen in January of this year, the UN published a regulation on automated lane keeping systems. And this was actually the first ever regulation published, which was designed so that the driver could hand over control from themselves to the vehicle system to take over the driving task. And this is actually a fairly momentous step. So this is the first regulation where we're allowing the vehicle to drive itself within certain situations. And it's really quite amazing they've done that with this regulation that fits into the current type approval system. So this is just another technical regulation that a vehicle can get approved to, such that it's able to drive itself. So does this mean that we can, you know, job done, we've got an automated vehicle and we can all hang up our coats and relax? But unfortunately that's not the case. If you look at this regulation, it's very limited in scope. So in the UK, it's limited essentially to motorways and at speeds of less than 60 miles per hour, which is 60 kilometers per hour, sorry, so about 40 miles an hour, a shade under, which narrows the system down to what is essentially a traffic jam pilot. And so the use case is fairly restricted, but on top of that, the driver has to be available all of the be able to take back control if requested by the system. So there is an underlying onus on the driver to be able to take back control within a given period of time, which is actually 10 seconds, to ensure if the vehicle encounters a situation which is outside of its design domain, that the driver can take back control in reasonable time. So even though this is a really momentous first step, it's still a long way from where we see the end goal of having highly automated vehicles that can completely drive themselves in a much more complex operating environment. And so even though this is just a first step, I think it's worth saying that there's been a lot of learning during the development of the ALKS regulation at the UNECE. So they've had, for a start, they've had to think about all sorts of issues which we know are going to be recurring issues as we move into higher levels of automation. So they've had to think about behavioral requirements, cybersecurity, auditing, all of these different aspects of the vehicle, which will be extremely important for automated vehicles that we classically haven't had to think about in vehicle regulation until relatively recently. But the other thing we've learned from the ALKS working group is how hard it will be to develop regulations for automation. So even to develop this regulation for the limited scope took around 3 years at the UNECE working group, and at the beginning it was a much more ambitious scope, and they ended up having to narrow it down to something that everybody could live with, to a point where we can ensure that the vehicle is safe within the entirety of its operating domain. But it's worth saying that there are currently discussions about how to extend the operation of the system to allow higher speeds and to allow lane changes, which would increase its number of use cases quite significantly. And the UK is co-chairing these sessions along with the European Commission and Germany, but that special interest group has only recently started, so we've yet to see how long it will take to finalize the plans for extending operation of ALKS. But where do we go from here? Even with the higher speed operation of ALKS, the scope is still relatively limited to just motorways, and in terms of the driver availability, there's still a long way to go before we really realize all of the benefits that we want to see from automated driving. And the headline titles would be the improved productivity, the accessibility to transport, and improved safety. So if we want to realize all of these benefits to the fullest extent, then we really have to start thinking about how to develop an approval scheme for very highly automated vehicles. And this is where projects like CertiCAV really fit in. And the CertiCAV output, which is being finalized now, is a really important and detailed piece of work on this subject. And it's really considered a lot of the issues that we're going to face when we're trying to develop an assurance scheme for highly automated vehicles. And the department certainly plans to take on board a lot of the findings that have come out of this project, and that will form the basis of a lot of our thinking in moving forward to approval schemes for these sorts of vehicles. So it's a very exciting time, and the CertiCAV output is certainly going to be very helpful for us in moving forward and answering that question of how we can, how the approval system is going to have to change if we want to include highly automated vehicles. So with that, I think I can say that we'll look forward to some very interesting discussions today, and over the next few years as we continue to work on this, as we undoubtedly will. I think it will be probably going on for more than the next few years. So I hope you enjoy the rest of the workshop, and yeah, I think I'll hand over to Zane, who's going to take you through the CertiCAV project.
Yes, thank you very much, Pete. So I'm Zane Seigel. I'm the technical lead for the CertiCAV project, and I'm going to give you a quick overview of the goals and scope of the project, and some of the technical work which the rest of the team will be going into in more detail later on in this webinar. So firstly, to note that CertiCAV is building on work we've done for the DFT on the music project, which was a proof of concept project that ran for 2 years and has built an open, onlinely accessible scenario database. And this is a demonstration of it running. We have an export API and the ability to sync local databases if stakeholders want to use the system in-house. This is built on OpenX ASAM standards, and it's also available open source at the link there. And we built up a lot of knowledge doing these projects, which we've put into good use on CertiCAV, where we have a significantly wider scope of safety assurance of highly automated vehicles, HAVs, by which we essentially mean SAE level 4 vehicles. Just to note here, we also, it's not purely safety focused, because we see there must always be a trade-off of safety against the progress that the vehicle can make. And clearly no one is going to buy an autonomous vehicle if it can only do 2 miles an hour, however safe it may be. So as an assurance process has to recognise that there's a little bit of a trade-off here. We've also restricted ourselves to the perception and tactical decision making of an ADS on what we're calling a nominally performing HAV. Nominally performing means basically that nothing is broken. We're not considering any functional safety assurance or failures. We're also ruling out of scope cybersecurity, operational safety, and in-use monitoring. We're very aware that these are all important topics, but we have had just 1 year finishing this month to deliver this project, so we've tried to address things that we can tackle fairly well within that time period. The outputs of the project are going to be a report we're just finalising, as Pete says. We're going to open source some software, and Rob is going to be providing a demonstration of some of this later on. And this webinar also is a key output to keep the community informed of the work we've done. So really on CertiCAV, we're answering the question, how do you construct a driving test for an autonomous vehicle? Because it's no longer a human driver that would undergo a human driving test, it's a HAV. And so to answer that, we really need to define properly what means good driving means. We have to have a testable set of requirements. And we've started off with these 9 performance criteria, where we've tried to enumerate everything that you would expect a HAV to be able to do. So firstly, and most importantly, is do not cause collisions. But then second on the list, we've got avoid collisions, even if they're not your fault. And I think this is quite an important aspect, that HAVs will probably be extremely good at not falling asleep and making mistakes that human drivers do. But conversely, human drivers are very good at avoiding a collision if other road users are behaving stupidly or not paying attention. And quite often a human driver can avoid a serious incident from resulting. So perhaps we'll have very strict requirements on the first criterion and slightly, say, a target of only as good as human drivers on the second, for example. And then we have these other 7 criteria, which I won't go into the details right now, but just to say that having listed these is only the start of the process. We still need to make this into something that's formal and testable. And then from an assurance point of view, we need a procedure that an independent body could use to ensure that these have all been met in a highly automated system. We've assumed a 3-step approval process. And phase 1 is the classical type approval, kind of system approval step, where we have the TAA, the Type Approval Authority, will be working closely with the ADS entity, which is the manufacturer, essentially, the organization that is responsible for the ADS and has submitted it for approval. We then have a second phase where we envisage the ADS being approved for a specific deployment, which is to say to operate within a specific geofenced area. And here it might be a traffic authority as well as, or instead of, a regulator who's doing the approving. And we've also used the terms user in charge, which the Law Commission have coined, which means a vehicle that needs a human occupant to take responsibility for things other than driving. Also, we have a NUIC, which is when there's no need for a human. And this corresponds to in the Koopman or automation modes, an autonomous system. But if there's no need for a human, then those other safety aspects, for example, making sure that everyone is wearing seatbelts, will have to be managed by a licensed fleet operator. So we see this UIC or NUIC route having different organizations responsible for gaining approval at this second phase. We then have a third phase, which is the in-use monitoring, and again with the ADSE and the UIC, or else the LFO, being the organizations that would support the monitoring process. On CertiCAV, we're focused only on the first phase, and we see that the second phase will have to take a lot of inputs from the first phase. So I think a lot of the ODD approval topics will have to be covered in phase 1, and phase 2 will just be a comparison of those ODD features against the geofenced area. Okay, this slide provides an overview of everything we've touched on CertiCAV. Starting at the top here, we have performance criteria, which are the 9 criteria I've just shown. And we also defined performance indicators, which are measurable quantities that relate to the performance of a HAV. Metrics, for example, time to collision might be one. We also need a threshold on those. What's an acceptable numerical value that you have to stay within? And these 3 together will feed into the requirements for the ADS. And then that will feed into the ADSE's own in-house safety assurance processes. We envisage there will need to be a strong organizational safety culture and safety processes within the ADSE. And they will also conduct a lot of V&V activities and testing to confirm the safety of the ADS. And both of those will feed into the safety case they would produce for the system. Then we would move on to system approval. We've defined a HAV super system specification, which is the vehicle itself and all of the other systems that contribute to its driving behavior. And you'd need some basic details about this to feed into the start of the process, as well as the requirements. Then the approval would look at auditing that specification, the organizational safety and the safety case. It would also likely conduct a certain number of scenario tests, both in simulation and with a physical vehicle, including very likely a check on the fidelity of the simulations that have been run by the ADSE. Finally, we also expect the short road tests to be part of this process. And just to say that I've gone through all this quickly, and my colleagues Tom and Siddhartha will be providing some more details shortly. Finally, to note that we've done quite a lot of consultation during this project. We've had an advisory group that have been very supportive and helpful. We held an initial workshop with them towards the start of the project. We've then had 2 public workshops, which are available to review on YouTube. We've met with a lot of stakeholders, and thank you very much to all of those we have met with. And as Richard said, we've had a very engaged steering panel consisting of the IBS team at the DFT, also the VCA, CCAV, Innovate UK. And we've been following a lot of the wider industry developments and publications, of which there have been very many. So that was my introductory section. I'm now going to pass on to my colleague, Tom Webster, to tell you about some of the nuts and bolts of the project.
Hello, everybody. Good to be talking to you this afternoon. So I'm talking to you about some parts of the CertiCAV framework, so system definition and specification, requirements, and system development. And so this first slide is really just kind of making sense of the title, really. So there's 4 parts to it: system definition, specification, requirements, and system development. And this is kind of showing how they relate to each other and why we've put them together. So for this framework we're putting together, we say that we need to identify the assurance use case. And then from that, you pull out who are the definition of who are the stakeholders involved, and what's the definition of the system involved in that use case. And then from that spans out how you specify and manage that system, and how requirements that are applied to that system are defined. And then, of course, those then relate to system development. So some entities developing the system, so on and so forth. So just looking at that first part here, identify the assurance use case. The use case we illustrate as follows. So there's a road traffic environment, and at the moment in that road traffic environment, we've got road users, we've got human operated vehicles, visual and digital infrastructure. These are regulated at the moment. So there's higher regulations, driver licensing, vehicle requirements that apply to human operated vehicles. And by assurance, what we mean by that is that it's predominantly safety, but not just safety, because higher regulations and rules do involve not just safety, but kind of cooperating with people, being considerate to people. And there is some consideration to being efficient. As Zane kind of mentioned earlier, that things have to be usable, and property protection. So there's this new entity being introduced into the road traffic environment, the highly autonomous vehicle, the HAV. And then our use case is this assurance framework for that HAV, satisfying this assurance. And so that obviously takes an input in from the Automated Electric Vehicle Act and from the CAV codes of practice that have been defined. However, there's also this two-way relationship with other regulations. So in terms of this existing fabric of regulations does feed into it, and there does need to be some feedback back into regulations and practice as well. So then kind of looking at the context applied here, we're introducing this HAV into the road environment. So this is our illustration of a HAV. No wing mirrors there because it's a HAV. So it's installed with an ADS, automated driving system, performing the dynamic driving task. So we're looking at safety assurance of the ADS integrated into this HAV that's performing the driving task. We're looking at level 4 automation. So we're not specifically trying to cover level 3 and looking at sort of HMI between a kind of an operator and the vehicle. We're trying to cover all of this as well. And an important thing to note, so there's several stakeholders involved in this deployment. And this is what we mean by this. So we've outlined an ecosystem that's involved in the use of a HAV on the road. So we consider three key stakeholders, being the regulator, the ADSE, and the technical service. That's because of our focus on CertiCAV, on the system safety and the system approval as per that kind of phase 1, 2, 3 that Zane talked about earlier. So there's the ADSE who's developing the system, the regulator who's enabling that system to be used on the roads, and then the technical service who's then supporting the regulator and inspecting the ADSE. And from a top level, the ADSE is making the vehicle for use by a user in charge or licensed fleet operator, but in reality, there's many different stakeholders who've got some kind of stake, either in terms of supporting the system or as a user of the system, that also have to be taken care of. They need a common definition of a common definition of the system to support, so that they can undertake their functions, or the system is explained that they can trust the system, so on and so forth. And so we've got a HAV, as mentioned before. So this is equipped with an ADS. It has data communications, this kind of features. And then we can actually then start looking at what it is, the actual definition of this automated driving system. So we've put in place a basic breakdown of the ADS, just so that there's a common definition, so things are explainable. This is generally aligned with PAS 1880, if you're familiar with that one. And one other term is that have behavior, so is a semantic description of the observable actions of the have. So speeding up, slowing down maneuvers, that's have behavior. So it takes into account vehicle dynamics. And the kind of things that need just to illustrate what needs to be explained in the common system definitions. So, for example, perception, what are the sensors involved, what is detected, how's the system localizing, live data sets. So, what kind of objects in map and communication data, what's their role in the system, tactical decision making. So, what maneuvers is this have intended to perform? Control is involving chassis sensor control systems, and data communications. So for instance, a key thing with data communications is, are there any safety critical functions that are being undertaken off the vehicle? And to really make sure this is explicitly taken care of, this is why we defined this have super system, highly automated super system, because the extent of the systems that are involved in the performance of this HAP behavior can extend beyond the vehicle. So if you've got a remote operator playing a role, they're not on the vehicle. So this is why we have defined this HAP super systems, to make sure it's explicitly included any off-vehicle systems that are involved. And just to illustrate that, so for example, GNSS plays a key role in that soft board. You can have data, HD maps, or updates. You could have a human performing some kind of remote role, or you could have a human on board. And just focusing on this human role is an example of how things can kind of be defined and explained and what it kind of means. So the position of the human affects which systems are critical to the human's functions. So if your human is on board, the human and machine interface on the HAV is critical. Whereas if they're off board, the data communications is also critical. Whereas the role that the human is playing affects what the operational functional automation level of the vehicle is. So something I just throw out there, and it would be interesting to see if anybody has any thoughts on this in the Q&A. So suggest that if a human is involved in the dynamic driving task, so tactical monitoring and being relied upon fallback, then the vehicle is not entirely being operated as a HAV. Because if it's level 4, well, the system is doing all the DDT. So it's not completely level 4. And this we call a mitigated deployment. So there's a HAS being developed by an ADSE, and various stakeholders need to be collaborated with in order to support this HAS being actually out in the wild, used on the roads. So a user in charge or licensed vehicle operator, they need to know what their system is. Does it satisfy their needs? What do they need to put in place to operate it? The regulator needs to approve the vehicle. The technical service needs to support that. Insurers need to provide insurance products. So they need to know what kind of risk they're taking on and covering. And there's various service providers who may also need clarification. So what we suggest there is that a specification of this HAS needs to be put together in order to facilitate all these roles. And we've identified 5 key areas that we think need to be included in the HAS specification. So vehicle operational characteristics. So effectively what is the class of this vehicle, and some top level things. The operational design domain is, of course, very important. ADS functionality, so this is covering what the perception performance is, what sort of maneuvers this vehicle is doing, how it's, so the ODD is the environment it's operating in, and the ADS functionality is how it's operating in that environment. The architecture, so around the have, what systems are involved and what they're doing, and deployment management. So this becomes important. So for instance, you might have a limited ODD, but your deployment management is affecting what is your understanding of how often you are going to be exiting your ODD due to weather factors. So just to give a bit of an example, what a specification might look like. So exteroceptive sensors could have a mapping and define what sensors are involved and what they're doing. HAS architecture could largely be involved in a flow diagram. This is an example we put together for a car parking chauffeur, and then ODD aligning with PAS 1883 would include these three top level attributes. So performance requirements. So a regulator is going to put in place some requirements as to is regulating this have and has. An ADSE is going to develop this and would need to make sure that these requirements are adhered to. And we've assumed that a system developer is going to produce a quality and safety argument with some evidence. And so something we've suggest is that for the arguments and evidence to be traced against the requirements, that you need common metrics between the two, and this is what we call performance indicators. And so talking about performance indicators, we have looked at those and some of the factors involved and identified 4 top level types of performance indicators. So number 1, event occurrence. So rate of occurrence of describable events. So for example, collisions, injuries, or object misclassification. Performance models. So these are kind of like real-time mathematical expressions of the system performance factors. So for example, modified time to collision or threat levels that are often used to trigger ADAS systems. Formal specifications are statements expressed with formally defined vocabulary, syntax, and semantics. So an example of that would be Intel Mobileye responsibly sensitive safety, or NVIDIA's safety force field. And then informal specifications. So those are specifications that do not satisfy being formal. And these are quite key because the existing road traffic regulations, rules and codes that are, of course, have developed over time to be an appropriate tool for regulating humans, because they haven't been put in place for the context of machines and you know, a verified and validated system, these are often not formal. And so just to give a bit of an example there of event occurrence, so quite often what's involved there is kind of traffic incidents, and one way these can be defined based on the kind of general a system that Haydn put in place quite a while ago, is that you've got a pyramid. Undisturbed passage is the main bulk of your total volume of driving, and then as you go up the pyramid, you increase in criticality. And then at the tiny top, you've then actually got your collisions, and then those can then also be categorized in terms of severity. So this is the Haydn system, and then we looked at that and put some figures to that one. So then looking at the relationship between performance requirements and system development. So there's a system being developed at a top level that involves quality and safety management. And then there's various processes forming part of that, including functional safety and safety intended functionality. And then an intended functionality specification, a specification of how this thing is intended to function, is put into that system development. And then in terms of regulation, you can regulate this in two ways. You can either have technical regulations on specifications, or you could put technical regulations based on what needs this system needs to satisfy. And at the moment, this is predominantly done through national and international vehicle requirements, through specifications. So for example, if this was an automatically commanded braking system, there's regulation 131 specifies specifications for that system function. On the needs side, there may be some things that there's some kind of failure rate limitations involved in functional safety, but they're not directly referenced. They come through via kind of QMS standards. So this is largely done based on meeting customer needs or managing organizational risk. And largely this is fine because vehicle manufacturers are large OEMs who want to maintain their reputation over a long period of time. However, when we start looking at the use case for CertiCAV, and you're looking at level 4 systems that are applied over a much wider domain, now you don't just have what is currently in national and international vehicle requirements. You're involved in the Autonomous Electric Vehicle Act, road traffic regulations, and driver licensing. These now need to be incorporated because you're taking over that human function that these are applied to, and suggest, I'm not really quite able to delve into fully explaining it right now, but suggest that it starts to become impractical to prescribe functionality when you've got this much broader remit. So now, rather than specifying an intended functionality, you need a process, which we call behavioral safety, of actually developing the intended functionality. And there's going to be some involvement of regulating the needs that are satisfied rather than jumping straight to prescribing specifications. Or looking at another way, if you were continuing to prescribe specifications, you need a more systematic process of putting those specifications together. So same problem is coming through a different route. And just kind of embellishing on that, so two things that are under our remit of behavioral safety that needs to be taken care of. So the HAV behavior needs to account for driving rules and codes, because there's no longer a human being relied on for that as a system. And the HAV behavior needs to be completely responsible for safe and effective driving. So this is no longer a level 2 ADAS system that just, as long as when it does decide to perform a function, then it needs to make sure that that is absent of unreasonable risk. It needs to make sure that the risk is reasonable at all times. And just providing a bit of an explanation on that one. So for that first one, accounting for driving rules and codes, this is our HAV here, and it's looking to pull out at a junction. It's having to find a gap in traffic. And if you do a strict interpretation of the highway code, you need to make sure that you're not causing any other road user to adjust their speed at all. but is that possible in all circumstances? If it's highly congested, does it maybe have to make this vehicle slow down a little bit? Is that reasonable or is that not? How are all these things weighed up? And so developing a codified highway code would help develop an understanding and help map how these aspects relate to intended functionality. Looking at the other one being completely responsible for safe and effective driving. So if we now turn this on its head, our HAV is now approaching this junction and there's someone coming out. Now, if you apply the risk state machine from functional safety, this talks about, okay, some failure occurs and there's a hazard. And if we try and pull that out of functional safety domain and into driving task, so this hazard is this vehicle pulling out here. This triggers the control action when there's a driving situation present. So when it's actually starting to incur into the driving path, at this point, it's now triggering the control action. This is active safety, and this is fine for lower level automation systems where it's just if the human driver has missed something or isn't paying attention, it's just providing some fallback of the human. But this isn't how a good, careful and competent driver performs when they're taking full responsibility for the driving task. You're not going to wait until your lane is being incurred before you start to take action. So we suggest under behavioral safety that you need to add more, it's not just active safety, but there's this element of tactical safety. If you're taking full control of the dynamic driving task, you need to be in control of the hazard exposure. And so at this point where the vehicle is incurring and it looks like they're turning right, you've got a challenging condition starting to incur, and you can take action, you can start to slow down to prevent that hazard from actually occurring and avoid this situation of having to employ emergency braking when they're actually incurring your lane in front of you. So then moving on to actually defining performance requirements, having sort of talked about some of its various relationships and various parts. As Zane mentioned, our work is built upon previous work done in music, and as part of music and the work there, driving performance criteria, this idea was formed, and these we consider still to be useful as a tool for identifying and verifying a set of requirements. And in terms of actually putting together requirement statements that support all of the aforementioned, so we talked before that they need to reference performance indicators. So here, this example, one example is referencing injury collisions. And then there's then three components we've identified for the requirement statements. So the first one is the conditions. So in this case, there's a condition of not causing. Limits, so there's a rate, a limited rate there. And certainty, so when you're actually rating this to a system development process and this safety argumentation and the evidence involved, that's where the level of certainty that you've achieved becomes involved. And then looking at how this might then relate to an actual definition of a set of performance requirements. This is just a sort of an example. This is not an attempt to come up with something complete. That if you have those 9 driving criteria that we've identified, you can then relate the top 3 to ones that are directly safety related. So making sure that the safety argument of the system is sufficiently managing exposure to risk. And then the ones below map to is predominantly based on cooperation and fitting in with the existing system of regulation of the road. So ensuring conformance to highway code. And then out of this, we get 3 if statements. So because the highway code is an informal specification and not a formal specification, it's possible that in the definition of the system, you identify that you may have situations where you may need to contravene a rule for the purpose of safety. And so on and so forth, for if it's conflicting with another rule, or if it's due to human conventions that are present in that system. And so these if statements, so that they could be removed. Specific cases of these if statements could be removed if, for example, these specifications are increasingly formalized and deconflicted, and also based on the system specification. So if the HAS specification is such that during the system development it's identified, you can follow all the rules and there's no issue with safety because it's a relatively simple domain and there's not complex potential rule breaking involved for the purpose of safety, then these then aren't applicable. And so in summary, so assurance is the safe and effective operation of the system in a multi-agent system. So we identify that there's an ecosystem of stakeholders. There's a common system definition, which is based on HAV, ADS, and HAS. There's a HAS specification that's managing cooperation between all the ecosystem, and then there are performance requirements with these 3 components to them, and that the system development provides a quality and safety argumentation and evidence, and there's performance indicators that are common metric between the 2 of them. So I'm just on time. I apologize that I have not fully explained everything. The idea of this was to give an impression as to the kind of content we're covering in the CertiCAV framework, and eager for any Q&A that you have for us to so that we can explain some of this further. And so okay. I'm handing, yeah.
Yeah, great. Thank you, Tom. Thanks also to Pete and Zane for the early presentations as well. Yeah, we're bang on time, so well done all presenters. So yeah, we're gonna give you a short break now, and it is a short break because we've got quite a lot to cram into the final hour. So please, yeah, see you back here in 5 minutes. Thank you. Okay, well, doesn't 5 minutes go quickly when you're staring at the countdown timer? Okay, well, I hope you all enjoyed the break. We'll resume again now. Siddhartha's from WMG. He's going to talk to us about V&V. So, Siddhartha, over to you.
Hello.
I can hear you now, Siddhartha. Just need to reshare your screen.
Okay.
Okay, there you go.
I am not sure why you don't see the full text. Can you see my screen?
Yes, can.
Okay, perfect. Very good afternoon to everybody. I'm Siddharth Kaski from WMG. I'm going to talk to you today about some V&V best practices and focusing on an ODD-based approach to the whole V&V process, as focusing specifically on scenario-based testing. So one of the things that I would like to mention is everything that we are going to talk today is actually building up on what we've already presented in the previous CertiCAV webinars, and also the work that Tom and Zane had presented earlier. So I'm not going to repeat everything that they've said, but I'm going to talk about the delta that's left within the CertiCAV framework. So from an ODD perspective, a lot of us are very familiar with the concept of ODD, are very familiar what it's for, but most of us tend to use ODD in terms of scenario generation, in terms of behavior definitions. We talk about ODDs as operating conditions for ADS. That's the general way the industry tends to use ODD as a concept, but a more subtle and more less appreciated concept is the use of ODD and the dependence of ODD on scenario completeness, safety metrics, and simulation requirements. I saw a couple of questions around simulation requirements. We won't have the time to go through that in this presentation, but if somebody wants to talk about that, we can have a session in the Q&A. I'm going to speak today about mostly around safety metrics and scenario completeness and the effect of ODD on those two aspects. A lot of us are fairly familiar with the concept of scenario generation. You can have a database approach, you can have a knowledge-based approach, you can use accident databases, insurance claim records, you can use approaches like STPA to generate scenarios, and then all the scenarios will end up in a scenario database, and then you'll use ODD-based labels to actually figure out the scenarios from your databases itself. So that's all we already know of right now. So what's new right now? So when we talk about the whole concept of ODD and the interlink with scenario-based testing, you add ODD to what we call as a behavior library that Tom was mentioning earlier. And what we get is a fairly high-level qualitative scenario, which can then be developed into a logical scenario and subsequently into concrete scenario. The bit that has not yet been answered from the research community and the industry side is the last bit over here is around test case metrics and completeness, and that's where we're going to talk in a bit more detail in the next couple of slides. I was just trying to think about this in a slightly taking a step back from this. If you talk about the whole safety assurance process for CAVs, essentially there are only three things that you need to do. You need scenarios, environment, and safety evidence and safety argument, which essentially boils down to the fact that you need to create scenarios, format scenarios, store scenarios. You need to plan and execute them in a particular environment, and ultimately analyze and decide. So what we're going to talk now is the last bit around analyze and decide. Rest, a lot of that has been spoken already. How do we go about analyzing and decide if the safety assurance process, if the CAV is a safe CAV based on the scenario-based testing that we have done? So in order to do that, we go back to the driving criteria that Zane and Tom have been talking about. So as part of CertiCAV, there have been 9 driving criteria that we have been identified. These essentially are behaviors. So you're talking about a CAV not causing harm. That's actually a behavior of a CAV. So what we do over here is, let's consider this behavior in a controls engineering problem. So this is controls engineering 101. If you consider driving task as a control problem, so the control process is the driving task, and the control algorithm is the autonomous control system over here. So the autonomous control system, for everything it does has an assumption and a context associated to what it's doing. Based on that assumption and that context, it is actually giving out a control action, which is driving the vehicle forward, which is actually doing the driving task. So now let's overlay this concept of controls engineering onto the driving criteria that which we've identified as part of this project. So we've got 9 criteria. We'll use an example of one of them, do not cause and harm, and then we'll explain how you can use the combination of controls engineering and these driving criteria to not only identify scenarios, but also to identify pass-fail criteria, which again become your metrics down the line. So let's think about it in a way that every high-level criteria that we have, so do not cause a harm, is actually a fairly high-level driving criteria. What does it mean when we try to use that in a simulation-based, scenario-based testing flow? So if we think about do not cause and harm, and if we apply the controls engineering on top of it, it means that we need to have a set of assumptions, we need to have a set of context or conditions. So for this driving criteria to be true, an assumption, and right or wrong, a possible assumption could be that the ego follows the rules of road, and it also means that others are following the rules of road. Only when this assumption is true would this driving criteria be satisfied. That could be one of the assumptions. Having said that, we can also say this is only true if the context is that the ego is within its ODD, within its operational design domain. So with these assumption and context, we're saying that this driving criteria is true. Now let's try and apply that in terms of a scenario-based approach. So let's say my goal for my driving task right now is an unprotected right turn. So an unprotected right turn is my goal. So my assumption right now is that everybody is following the rules of road. And a possible example over here could be that everybody will wait at a red traffic light. That's my assumption. So if that assumption is not true, I cannot satisfy do not cause and harm. So the context here, or the ODD here, would be a crossroad with no traffic light. Now, given this assumption and given this context, in order to perform this goal, my expected behavior from a CAV perspective would be, I need to have an indicator, I need to drive forward, I need to wait, observe, turn right. All of these maneuvers together are expected, and only if I do all of them will I actually pass that scenario where I'm testing an unprotected right turn behavior. Now, let's add a bit of complexity to this. Let's add in the context a bit of disturbance. Let's say there's a tree falling in that particular context. So my goal is still unprotected right turn. My assumption is still that everybody will stop at a red light. And my context is that I'm actually at a crossroad with no traffic light. The expected behavior remains the same, but there's an additional behavior that is required from an ego perspective where I'm actually mandated that I need to prevent a collision. So in addition to indicator, drive forward, wait, observe, turn right, the additional behavior that I need to do in order to pass the scenario is that I need to prevent a collision. So what does it mean in terms of a scenario generation process? So now I'm saying that for a given ODD, under the conditions that the rules of everybody around you will follow the rules of road, my expected behavior is indicate, drive forward, wait, observe, and turn right. And as a result of that, I should not be causing any harm. Now you can use that behavior and ODD together to actually create the qualitative scenarios, because as we've earlier said, that location plus behavior will give you the scenarios. So that's a way to get the scenarios, but that's not enough. That's not the magic over here. The magic is actually when you try and think of the pass criteria over here. From an ADS perspective, for this particular scenario for an unprotected right turn, for it to pass that scenario, not only do you need to check for the expected behavior of indicator moving forward, waiting, observe, and turning right, but also you need to check for not causing any harm. And the more interesting bit over here is all this is only true if and only if the assumptions that you had for that driving criteria are true. Now, those assumptions are not the pass criteria for the ADS. They're actually a pass criteria for the simulation that you're executing. And that's a very subtle difference most of the times we tend to focus on the pass criteria for the HAVs or the automated driving system. Whereas it's equally important for us to focus on the pass criteria for simulation itself. Because if those two do not match, then there's no point in actually doing the scenario-based testing and the simulation-based testing. So what we're trying to show here is from a very top level, abstract driving criteria, we've been able to derive from an ODD-based approach the exact concrete scenarios that you want to execute, but also the pass criteria for your automated driving system, as well as the pass criteria for your simulation. And these two together need to be considered when we're actually doing a simulation-based testing approach, or we're doing scenario-based testing. Most of the time, it's only the pass criteria of ADS that are taken into consideration. So in summary, what I wanted to mention was, I think there's a lot of appreciation around ODDs and the role of ODD in safety assurance, but there's not enough appreciation of ODDs and its importance in safety metrics and testing completeness. People tend to think that ODD has no role to play in those things, and actually that's something that we are trying to move over from a CertiCAV perspective. The other very important aspect that I wanted to mention here was a scenario pass-fail is essential when you're talking about scenario-based testing, but it is equally essential that we ensure that we check if the intended scenario that we wanted to execute got executed or not. Because if that didn't happen, no, it doesn't matter if your scenario was pass or a fail, if the intended scenario did not occur. So we need to increase the appreciation for the latter, and ODD has a big role to play in the latter, because it actually gives you the assumptions under which you need to observe your simulation based testing. And at the end of the day, I would say, I think this is something I say after every presentation, is no one organization can do this. And there's collaboration needed, there's knowledge sharing needed, both nationally and internationally. I do see quite a few international participants on the call. So we need to work on this together, and that's the only way we are going to sort this out. With that, that's all I have from my side. If you've got any questions, we'll take it at the end, and I'll hand over to Tom now from Connected Places Catapult, who will talk a bit about safety assurance.
Hello again, I'm just bringing up my presentation. So yes, I'm back again, this time to talk to you about independent assessment against requirements. And again, this is pretty brief. I'm being very selective here and just picking out a few bits and pieces because I'm doing this in a tight time slot here. So before kind of we sort of set out that we've got this HAS and that there's an AGSE developing it, and assume that they're producing a HAS specification and a system safety case. And then there's a regulator who's enabling this has to be used on public roads, and they have requirements. So what the system approval is all about is that there's a technical service who's going to be looking at all of this and checking it against requirements and doing an assessment and feeding that up to help to be part of the system approval. And one thing that we've identified as part of this is the concept of having a deployment risk classification. So something that's going to be a challenge is there's going to be quite a wide array of systems, big and small, complicated and less complicated, and making sure that the system is proportionate to the risk and the size of the system, that it could potentially be managed by something like this deployment risk classification. So the idea here is that if you have a matrix like so, which can have different attributes. So for example, severity class. So this could be linked with the maximum severity consequence of failure for that particular system, and that could reference that there's standard references for that. So, for example, this is J2980 that just looks at velocity deltas and what potential maximum severity is associated with those. So if you've got a low speed system and you're not hitting, and it's effectively impossible for you to hit these deltas to have that severity, then you've got a lower risk, and that could potentially have smaller coverage. Deployment scale, so your risk is proportional to the scale. So if it's only doing 1,000 kilometers a year, maybe it doesn't require as much coverage as if it's several million kilometers a year. And then the complexity, so this could look at how complicated are the maneuvers, how complicated are the perception systems. There can be classifications there. So the general idea is here that you'd have a matrix like this, and then that could have, that would then relate, in this instance, an A to G rating, and that it's not going to change what the requirements are, but it could change what the coverage is in terms of number of scenarios tested, for example. So that's one idea to help manage making an assessment proportional. We've outlined an assessment process, which is summarized in this table. And so there's steps. Each of those steps is associated with an assessment activity. This is a top level description of the objectives associated with those. And so the first step is to check the HAS specification and do a safety check. So what's being looking for there is that the system has been described sufficiently that everything appears to be correct. This could involve factors such as have the people who need to be consulted with, have they been consulted? And this would also be helpful for doing something like that deployment risk classification. Actually, then there's some initial information that the assessment process can then be prepared and planned out based on that. Another one, the next one, road test. So the road test doesn't necessarily need to fit in the order it is here. It could be later, but an advantage of doing your road test relatively early in your assessment process is it's something that's the general presumption here is that what we're looking at here is that this is a level 4 system, and you're actually looking for the approval to operate this truly as level 4 system. So it's already been out on the road doing trials and beyond. So it's already been used out on the road. So why not do a road test where you're still going to have the same mitigations in effect that when you were using it on the road, and then it's an easy way of assessing that the deployment management processes are in place, that the system does, the driving system does appear to have the correct competencies, and gives confidence to then proceed with the rest of the assessment process. Because the amount of resource and cost involved with the road test is lesser than some of these other steps. Audit inspection, so the organisation doesn't need to be looked at. Is their safety management system, does it appear to be sufficient, etc. Looking at the evidence. And then from these steps 5 and 6 are then involving independent witness testing. So generating a set of relevant scenarios for the system under test, and then looking at it in terms of test bench, physical testing, and fidelity checks. So this is both looking at the performance of the HAV system in terms of is it safe, is it sufficient, but also in terms of the tooling and the facilities that have been used. So is there evidence there that things are sufficient to support the safety argumentation that's been put forth. So we have put some high-level definition on what's involved in these activities. I'm not delving into that in this presentation due to time constraints. It involves kind of methodologies and specifications, and it's quite dry and hard content to go through in a presentation anyway. But we are hoping to get something out there. So it's an initial system to be developed upon. But something I just did want to pick up on was, so there's this scenario generation plays a key role for both physical and test bench. And just to highlight that this is challenging. So generating scenarios is challenging for a system developer, but it's still challenging in the context of independent assessment. In some sense, there's an increased challenge, because the challenge for independent assessment is that you are picking a relatively small number of scenarios, but you still need them to be effective, and you still need to avoid gaps. And what this diagram is showing at what I just want to pull out of this diagram from a high level is that the system, the HAS specification is useful in this context for providing an input so that relevant scenarios can be filtered, and that also that there's utility in having a knowledge base that's built up over time of scenarios, of parameters, so that the relevant scenarios can be generated, and that this does also link in with a wider system of that there's a relationship between ongoing monitoring after a system's being approved and the body of knowledge that is then feeding into the know-how for independent assessment. And so in general, we see that all your know-how and your knowledge to do an effective independent assessment isn't necessarily going to be in place on day one. It's about having a process of building up over time and maturing it. And then that then leads on to my next slide, which is that of that knowledge management, so that we've identified that that there's this need to create and continue to improve a body of knowledge for HAV assurance, and that there's 3 areas that this could be considered in. So one was, as just mentioned, the scenario database. So in terms of logical scenarios, parameter distributions, that there's a need to have a common system for that. And then in terms of learning, so audit inspection knowledge base and good practice. And there's also techniques and tooling that are then supporting independent assessment. So modeling capabilities are required, assessment techniques, techniques for profiling, selecting scenarios, and so on and so forth. So that really was very brief, but that's just to give a general high-level definition as to what our approach is and the kind of content that we're covering. So I'll then handing over to Rob, who's talking about proof of concept in simulation.
Yes, I'm Rob Myers, part of the team here at the Catapult who's been working on the CertiCAV project. Just to set a little bit of context for this proof of concept exercise, the idea has been to take a few of the ideas which Tom and Zane have already explained and demonstrate them using in simulation. As you'll have gathered by this point in the session, there's quite a lot of things which need to be done part of the insurance process. We've decided to focus on one which is a bit unique to AVs, and that's the testing of tactical decision making in simulation. And of course, as with the rest of the project, we're assuming nominal performance, so we're not thinking about hardware failures or things like that. I think there are really three main things which make this problem interesting and challenging. The first is that people sometimes want this kind of simulation testing framework to solve all of the problems. And it's a really powerful tool, but it only goes so far, which means we need to put some boundaries on what it can and can't contribute to our assurance objectives. Secondly, requirements. Tom's presentation earlier made a lot of progress in getting from the fairly vague driving performance criteria to well-defined requirements. These still aren't things we can measure directly though. They relate to things which should or shouldn't happen after deployment. For pre-deployment testing, we're working in a slightly different environment. So effectively what we're doing is designing an experiment which should give us some evidence on whether the requirements are met. And finally, arguably the main reason we're working in this area is that it's not been done yet. But that means that things like standards and various tools which you might ideally want to use don't always exist or are in their relatively early stages. So to hopefully make a start, the three types of test which we've implemented, which will hopefully provide and then we're going to demonstrate everything in the context of an example scenario. So let's start is implementing expressions. So something that we think automated testing will do really well is when you have one of these formal specifications, checking whether a vehicle complied with it. This point probably sounds a little bit obvious, but you can't ask a machine to make subjective judgments about whether the specification that's being given is correct. And that's slightly problematic because, as Tom pointed out earlier, we're not going to have a formal specification for all aspects of good driving anytime soon. So we're accepting that there's probably going to have to be a certain amount of human judgment still involved in vehicle approval, but that will happen outside of any automated testing framework. What you can do fairly systematically is to compare one ADS to another system. So if you define a performance metric, you can put two systems through the same set of tests and just see which gets a better score against that metric. I think you need to be quite careful doing this for reasons which I'll mention later, but it can definitely be done. And finally, I'm definitely not the first person to say this, but it's not really possible to cover the entire input space for an automated vehicle in pre-deployment testing. What you can do is significantly reduce the risk of your deployment by carefully choosing which bits of the space you do cover. But there's always going to be a certain amount of risk that you discover something new for the first time after a vehicle's been let loose in the real world. So taking those things we can do and having a look at them in the context of Tom's example from earlier of a possible requirements framework, there's a few bits here I'd like to pick out and highlight. So the first is harm. Harm is measurable. There's quite a lot of literature out there about estimating the harm caused by different kinds of collision involving different kinds of vehicles. So it's fairly straightforward to produce a metric. What's more difficult is saying what level of harm is acceptable. And I'm not talking about the philosophical question of how safe is safe enough. I'm talking about the very practical question of, in a given situation, was this a good outcome or a bad one? I find it hard to imagine a formal specification for that, and I think that probably steers my thinking towards the reference model approach. The next slide has drawn this as an informal specification on the diagram here. And that's how the world of civil and criminal law works at the moment. But there's also been quite a lot of work on specifications of this sort of thing. Also mentioned the examples earlier of Mobileye's RSS and NVIDIA's safety force field. So I do think there could be a role here for formal specifications in determining causality. And finally, we've got the highway code. That's definitely an informal specification at the moment. There are probably bits you could formalize, but not all of it. And if these exemption concepts are needed, some of which could still be needed with a formalized specification, then you'll need a certain amount of risk assessment and human judgment to be involved in the process. So what does that mean in terms of defining tests? Well, I said earlier that we wanted to produce evidence that the requirements are met, and these are our 3 ideas on things which we think could help to do that. Let's start with the collision responsibility specification. To link things up here, we started off with a driving criterion of do not cause harm. Tom's presentation then went through how you might formalize this into a requirement which includes conditions and limitations. And now this slide is about defining what do you actually measure when you put the vehicle under test. One thing that is also worth mentioning is linking this to Siddharth's presentation a second ago, where he talked about having to set the conditions under which a particular requirement applies. The language on this slide are reasonable assumptions, but it's very much the same idea. What are the reasonable assumptions which a ADS should make in order not to cause harm according to those assumptions? And I think it's also worth just highlighting that one advantage, if you do go down this formal specification route, is that you can do quite robust testing compared to other types of specification. So you can measure a lot of scenarios automatically, and you can also do things like adversarial testing, where you try and effectively catch the vehicle out by testing edge cases of the specification where the compliance was marginal. The middle item on this slide is basically every other formal rule which doesn't fit into the first category. The reason we've these formalizations of the highway code effectively. The reason we've called it cooperative is because quite a lot of the highway code isn't about stopping you being responsible for a crash. It's about smooth traffic flow and managing the risk of other people's mistakes. Rules like the ones in the highway code weren't designed around automated vehicles. And that means that it's not and that means, as Tom pointed out earlier, you may need these specifications, these exemption criteria. What we can automatically report using a testing framework is whether or not the vehicle conformed with a given set of rules. And then you'll need some sort of subjective process outside of that to decide whether the non-conformance was acceptable or not. And finally, we've got this idea of comparing a particular reference metric to a reference model. You sometimes hear people talking about avoiding accidents which are preventable, which is actually really quite hard to define. What's preventable depends on what making inferences caused on it, which starts to get quite close to individual manufacturer specifications. So what we're saying here really is that you should avoid accidents which would have been preventable for a reference driver, or at least you should avoid outcomes which were worse than your reference driver. And that's one way of tackling the sort of avoid harm, even if not causing it. There are a couple of challenges associated with this. I think the key one is on here, that you might force your ADS to follow a reference model too closely. If you say that you should avoid any accident which is avoidable for a reference driver, then you also have to be very careful to make sure you're not creating situations where the reference driver does something which is normally wrong, but because of something very specific about that scenario, happen to be right, and that everyone else could be forced to copy it. And for that reason, there may well be a case here for making statistical comparisons across a set of scenarios rather than on a per scenario basis between the reference model although we haven't implemented that yet. So hopefully that's given you a good overview of the thinking behind what we've been doing in this demonstration packet. Get on to showing an example scenario and the software. I'd like to mention one of the practical considerations for implementing something like this. If you imagine you're a regulator and you're trying to check how an ADS will perform in a particular case, because you don't have access to a manufacturer's tooling and systems, you might want to ask the manufacturer, or the ADSC, as we're calling them, to demonstrate some scenarios. And you want to see what actually happened in the simulation, not just the report which says that the outcome was good. And that means there are two interfaces. You've got one on the way into the ADSC and one on the way out again. And the one on the way in has already been the subject of some standardization efforts, in particular a SAM open scenario, which at the Catapult we've had some involvement with. And that gives you a standardized format for sharing your scenarios with a third party. But when you want to get raw data back, I think the standards at the moment are a little bit less clear. For the purposes of our system, we've been using a format which we've internally nicknamed CertiTrace. It's not entirely new. In fact, it's very closely aligned with the SAM open simulation, with a couple of additions for things like a record of any collisions which happen in the scenario and some administration on which data need to be populated. Some of those will be very straightforward, but it does also depend on the requirements and the measurements which you want to make about the scenario. Types which I talked about in the context of the scenario we'll be using for the demo today. Our vehicle under test in this scenario is the one we called Ego. It's driving up the main road, and the Challenger vehicle is going to pull out in front of it. And we're going to apply one example of each of the three types of tests to this situation. First, we're going to check whether there were any collisions, and if there were, whether the Challenger pulled out close enough to the Ego to be considered at fault. Another way of saying that is that the Ego can assume that the Challenger vehicle won't pull out right in front of it. If it doesn't make that assumption, it can never pass the junction without risking causing harm. Then we're going to check all the other road rules. So the one we've implemented is at the moment is a very simple check of whether the Ego vehicle was obeying the speed limit. But I think it's also interesting to think about the second case, which is where we talk about causing inconvenience to the Ego. And that's because when you look at the definition of the give-way legislation, the legislation associated with the give-way junction in the UK, it actually goes well beyond simply putting the Ego in a position where it can't stop, and it goes to a level of causing inconvenience to the vehicle on the main road. So if you implemented this test as part of a cooperative driving specification, if this active vehicle pulls out in a way which is inconvenient or inconsiderate, but not unsafe or likely to lead to an unavoidable accident, then you would say that that vehicle has been non-compliant with the specification, but you'd also be saying that if there was still a collision, that's something that the Ego vehicle doesn't bear some responsibility for that. And finally, we've implemented a reference model comparison. So in this case, our reference model is Sam, our software developer, who is driving the Ego vehicle along. And what we're looking at is where the Ego crashed, would the outcome have been better with a human driver in the same situation? And as you'll see in a second, the answer is very often going to be yes, because for the purposes of demonstration, our Ego vehicle doesn't really respond to the Challenger vehicle at all. So without anything more from me, I think it needs to hand over to Sam, who will take you through the software architecture we've implemented and then show an example scenario working.
Hello, thanks, Rob. Yep, that was really interesting. So hi, my name's Sam Nichols. As Rob said, I'm a software developer here at CPC, and I've been working on work package 3 of CertiCAV for about 3 or 4 months now. So what I'm going to do is I'm going to take you through the software architecture and then take you through a quick demonstration and video of the program that we've implemented. So essentially what you can see here is the architecture that is loosely based on. So in the center here, we have a master script, which essentially controls all the communication between each of the different modules and yeah, just controls everything really. So first off, we have a database query. So this is where you want to define what sort of scenario that you want in your that you want to test. So this might be scenarios that drive on the right, scenarios that drive on the left, that sort of thing. So we input that query into music, the thing that we've been talking about. So Zane and Tom have been talking about. This music could be swapped out for something else, but it's generally a scenario database. So in this scenario database, once we've queried it, we then try and get some concrete scenarios. So to explain concrete and logical scenarios very, very briefly, logical scenarios are defining a scenario using an open drive and an open scenario, and having some parameterized values in that. So that might be how fast the ego goes between 0 and 60 miles an hour. So a concrete scenario would say, okay, drive at 45 or 30 or 20. So each concrete scenario is varied, making different sort of scenarios, even though the base scenario is the same. So yeah, moving on across that diagram, we then load in the open drive and run the open scenario in the simulator. For us, we're using Carla. This could again be swapped out for something else. But yeah, just for our demonstration purposes, we're using Carla. During each time step, we're getting out a raw data output, so like a ground truth almost. So this is like positional data, orientational data if there was a collision. And the output file, that is in the format of CertiTrace that Rob was talking about earlier. So once we've run through all of these scenarios, we are left with a load of CertiTrace files, one for each scenario that we've run. We send that back to the test management script and then through to the run tests. So this is the 3 tests that Rob was talking about. There's speed test, the pull-out test, and the severity test. So yeah, once we've run through that, we get an output result of either a pass, a non-compliant, or a human trials are required. So obviously pass or non-compliant, we generate a report and say if the ADS has performed well or not, and non-compliant and so on. If we do require human trials, then we have a human perform the same scenarios, the same concrete scenarios, and see and compare how the human compares to the ADS, and then generate a report based on the comparison and see if the ADS passes. So if I just quickly try and share my screen now, just to try and give a live demonstration. One moment. Oh, I apologize. I am not sure if I've selected the correct screen. Could someone help me out? Yeah. Are you seeing music now? Oh, sorry. So I've gone the wrong screen. There we go. Are you seeing music now?
Yes.
Excellent. Thank you very much for that. Sorry, Rich. Okay, so what you're seeing now is music. You're seeing all of the scenarios in music. And what we're going to do is just to give you a demonstration, we're searching in a query string, and we're receiving one logical scenario back. So essentially, we want to run our master script. This is presenting us with, do we want to run the scenarios and output the raw data files and run the tests, or one or the other, or run human trials? So for our purpose, we're just going to run scenarios and run the tests, input that same query string. We're going to download those concrete scenarios that I was talking about. And as you can see, we've got 5 scenarios from that. So in a moment, Carla will be initialized, and we'll start running those tests. So yeah, as you can see, the Ego is driving along on the main road, and at some point the Challenger vehicle will pull out. This is varied between different concrete scenarios. So as you can see, the Challenger vehicle will pull out at different times. Those two look fairly similar, but I promise they do pull out at separate times. As you can see, that one was way before. As you can see, our ADS is fairly awful as a demonstration, just it's driving at a constant speed. So from this, the main points are to take in that from each time step, a ground truth is being output, so CertiTrace format is being output. Videos are being recorded of each of these trials, and test results will then be run on all 5 of these scenarios. So as you can see here, just on the last one, so there's concrete scenario M129-3. So that was a pull-out test and severity, and the speed test is just above that. And then M129.4, speed test, pull-out, and severity test. So for this, we had our report will not be generated because one or more of the scenarios will require human trials. So just now, I will show you a recording, just in the interest of time, of our human trials and ADS trials as a comparison. So here you'll see this is an ADS driving along. This is the same logical scenario, but a different concrete. So as you can see, it just crashes into the back and yeah, just carries on driving. So it's not a very good result. So to compare, we have our human driver just about to come into the scene here. So this is controlled by a keyboard input on the top right here. And this is a human driver coming along. The Challenger pulls out, the human stops, avoids the collision, and obviously performs way better than the ADS. Again, this is just a comparison between the two. So human driver stops, ADS just goes into the back of it. So after this point, the results for these two are compared and a test report is generated. So I'm just going to hand back to Rob now to talk through that report that is generated.
Hello, yes. Just in the interest of time, I'm going to pick out a couple of things which I think are most likely to be of interest in this report. So things like the speeding test give fairly unsurprising results. I think the more interesting ones are things like this collision responsibility test. So if we look at this one, number 2, we're comparing, this is the one which Sam has just shown the human comparison with. In this case, the pull-out vehicle definitely behaved unreasonably, and the Ego vehicle can't be assured of stopping it. But what this does show is that the benefit of using this reference model of Sam could comfortably stop before the collision, and therefore got a much better score, and that allows us to make some judgments about how we perform on these more general issues. I'm happy to answer any further questions about this test report in the Q&A session, but I think for now I'll hand back to Richard.
Yes, thank you, Rob. Okay, so we're moving to the Q&A session. So I guess if the panel can all come back on camera, and additionally we're joined by Mike Brasher from the DFT on panel as well. So if we've got 5 minutes left, I'll let you go away on time. So we'll try and get through a handful of questions. But as I said earlier, we will download all the questions afterwards and issue written responses to all of them later. But maybe if I could start with a question for Mike, if I may, which is about existing products. So how are existing products on the market with automated driving functions or ADAS, let's say, how are they regulated today?
Yeah, thank you, Richard, and good afternoon to everyone. I think you partially answered the question through asking it, and effectively what we see today is advanced driver assistance systems and not automation on the roads. And indeed, the current type approval framework doesn't accommodate automation. what it does accommodate is some quite advanced driver assistance features, such as advanced emergency braking or lane keep assist systems. But the fundamental principle is that the driver remains responsible for the driving tasks. So the system is designed to complement and assist the driver and not take on full responsibility. And that's the crux with automation. We are expecting the vehicle to perform the role of the driver and act safely at all times. So I hope that answers the question.
Great, thank you, Mike. And then we'll go to Siddhartha, because you were very quick to claim this one, the Q&A, Siddhartha. I think it was probably an accident, but you can answer anyway. So what's a process followed to check simulation fidelity? And is there any criteria defined on the percentage of fidelity comparison?
Yeah, thanks, Richard. It's a hard question. I didn't want to answer this, so I'll try and answer this. I think the answer to this is it depends on what you're trying to achieve with the simulation. So if you're using things like simulation to test perception, your fidelity requirements would be very different as compared to if you're using simulation to test things like planning. And also the way you set your simulation up. So for example, you could go behind the sensor, or you could go in front of the sensor to test the autonomous control system. So there's no single answer to it. It's something that's also being discussed at a UNEC level right now. And the general consensus is, depending upon the way you set up your simulation system and what you're trying to test, the metrics would differ.
Okay, thank you, Siddhartha. Zain, I'll come to you next. So how important is it to have physics-based sensor simulation compared with ground truth sensor simulation? And are there any recommendations to use physics-based sensor simulation in a scenario?
Yeah, I don't think we're making any specific recommendations in CertiCAV. I mean, this links into Siddhartha's answer to the previous question, I think, and what kind of sensor modeling you need will depend on exactly what you're trying to test with that set of tests. But from my personal point of view, I think feeding ground truth data into the decision-making algorithm is much less likely to give you useful results. And I think you don't necessarily need a full physics-based sensor model, but you do need a sensor model that behaves somewhat like reality. Perhaps you inject noise or you inject false negatives, false positives, rather than just feeding ground truth in.
Okay, thank you. Now, we'll stay with you, Zain, actually. So how are things like harm, reasonable, considerate, etc. in the 9 rules defined? Because they may be open to interpretation. So
this is very hard to answer quickly, but I'll try. I think this is a large part of the time and effort on CertiCAV has come to we spent on trying to address this, and we're very aware that these 9 criteria aren't immediately testable, but we've tried to develop an approach to go from those criteria to things that are testable. And there's always going to be a little bit of a gap. And this is partly down to the gap in, as came out today as well, there's a bit of a gap in the formal rules of the road. They're designed for humans, they're not designed for autonomous vehicles, and they're not specified in a language that can be programmed or even tested against. So you may have to fill some of that gap by testing proxy measures on a statistical basis, but not all of that gap. So this is why we were defining the idea of developing performance indicators and thresholds against that can be used to kind of knit a coverage blanket around the driving performance criteria. To try and answer that shortly.
Okay, thank you, Zain. And then let's make this the last question for today for Tom. So the start point's been the vehicle. How much has been done, if anything, with the network community regarding things like V2I and data management?
Yeah, so we are somewhat vehicle-centric in what we've looked at. I think the bottom line is that these things are not at the level of detail, have not been defined in good practice or best practice. So at the moment, the discussion in terms of what is, for example, the role of a remote operator, what's the function of a safety critical system over wireless is not defined. And so we're starting with the fundamentals. We're only really covering the fundamentals in terms of it needs to make sure that if you are involving an off-vehicle system in some kind of safety critical function, that needs to be specified. Then once that is specified, exactly how that's handled and what's reasonable or not, I think that is something that needs further development in the industry.
Okay, great. Thank you, Tom. Okay, so I can see it is 4 o'clock. I can see some participants are having